Hidden more than 10 billion light-years away lies TON 618, a black hole so massive it defies imagination. But only now do we truly understand how powerful it really is. Its energy output dwarfs entire galaxies. If you enjoy cosmic mysteries, please subscribe and share, and tell us in the comments, do you think anything in the universe could rival TON 618's power? Thank you for watching. Now let's begin. The early universe is young and bright and filled with fresh matter that is still in the process of settling into the large-scale patterns that later will become the more familiar cosmic web seen in the nearby universe. But at this stage, the filaments of gas and dark matter are richer and more dynamic because the reservoirs are still full and not yet drained by long cycles of star formation. The background temperature of space is higher than it will later become, but still cool enough for hydrogen and helium to be the primary raw materials out of which the first generations of stars and galaxies continue to form. Gravity collects matter into halos that merge frequently and rapidly changing mass scales on short cosmic timescales, and these halos become the sites where gas can fall into deeper potential wells. The first large galaxies assemble their stellar content layer by layer as new stars ignite in pockets of collapsing gas, but the star formation efficiency is still evolving because heavy elements are still rare, and cooling primarily depends on simple atomic transitions rather than the richer molecular pathways that will grow more common after many more generations of stars have formed and died. The radiation fields in this epoch are stronger because bright young galaxies and starburst events flood intergalactic space with ultraviolet light, and this ultraviolet light can change the ionization state of intergalactic gas across large scales. At this time, bright active galactic nuclei are widespread because central black holes inside forming galaxies have abundant access to raw gas, since the cosmic supply has not been siphoned away by long-lasting star formation and long-term feedback. The physics that sets the stage for extreme luminosity rests on the fact that matter is abundant and movable, and the gravitational build-up of the most massive structures proceeds with fewer constraints than at later times when gas supplies become depleted and feedback mechanisms interrupt accretion. The quasar epoch reaches its maximum intensity around this interval of time, and many bright nuclei shine across the universe. The object now known as TON 618 emits its light during this era, and that light travels through expanding space for billions of years, and the continuous stretching of waves makes the original high-frequency photons appear redder when they reach the observer. Because cosmological expansion increases wavelength while the photons travel, the spectral lines of distant quasars shift toward longer wavelengths. Without this stretching, the intrinsic spectrum would appear much bluer and higher energy than it does in its observed form. In this epoch, the universe is roughly 2.2 in redshift, meaning the scale of space is now more than 3 times larger than when the light was emitted. During this time, the supply of cold gas inside cosmic filaments is still high, and most of this gas has not yet been locked into small stars or ejected into intergalactic space. The heavy element abundance is not zero because the earlier stars have already exploded and returned processed material into their hosts, but it is lower than it will later become. These small but non-zero heavy element fractions allow gas to cool a little more efficiently than pristine hydrogen would, and this supports the formation of dense regions that can fall deeper into the cores of young halos. Star formation and black hole feeding both depend on dense gas that can lose enough heat to condense further, and so small adjustments to cooling efficiency produce large differences in the amount of accretable mass that can pile up in central regions. The violent mergers between galaxies are common, and are often highly unequal in mass-producing tidal features that funnel gas into the inner parts of galaxies. The gravitational shock of these interactions perturbs gas from stable orbits and forces it into new configurations where it becomes easier to compress. The cosmological environment at this time is not quiescent in any conventional sense, because the rates of mergers are high, and the characteristic separation between galaxies is not as large as at later times. The dark matter halo population grows rapidly as smaller halos merge and sink into larger ones, and this hierarchical evolution means that early bright active nuclei have large fuel reservoirs at scales that extend out to regions where the gas still streams freely along filaments that feed clusters. Bright quasars are a natural outcome of these conditions. They arise not from rare accidents, but from the routine consequence of rapid structure formation and plentiful gas supply. The universe is young enough that most gas has not been consumed, but old enough that the first stars have begun to enrich the medium. The energy density of early cosmic radiation and the high volumes of raw gas combine to make the radiative engines of active nuclei especially powerful. The observed power of a quasar is measured in luminosity, and this luminosity reflects the conversion of gravitational potential energy of infalling matter into radiation. Observing bright quasars in the distant universe and relating their emission to the available supply of gas and the underlying gravitational structure provides insight into how energy output is linked to cosmic conditions. The existence of very luminous nuclei is supported by the global environment because long-range matter flows still act across large distances, and because the conditions have not yet transitioned into the more disconnected state of the present era. It is not an isolated or surprising feature of this epoch that such objects exist. Instead, it is compatible with the fact that the cosmic web is still heavily loaded with cold gas, and that the most massive galaxies are still in the process of building their central masses through a combination of inflow and merger-driven supply. This time period is thus a natural arena for the formation and sustained fueling of extremely bright engines. TON 618 is an observational window into this stage of cosmic history, and the light that it emits carries the signatures of a universe still rich in material and still undergoing frequent large-scale interactions. The global properties of this epoch reflect the density of matter supply, the youth of stellar populations, the dynamic structure of evolving halos, and the overall availability of raw ingredients to power extreme sources of radiation. In the early universe, large-scale structure is already present and defined by gravity, operating over vast distances as the dominant agent that shapes the distribution of matter and creates the scaffolding on which galaxies assemble. And in this broad environment, gas does not sit uniformly, but traces the dark matter, filaments that stretch between protoclusters, in patterns that resemble long, continuous bridges of material capable of transporting matter across cosmological scales. These filaments are not thin in the ordinary sense because their cross-sections can span millions of light-years, and their densities remain higher than the average density of the intergalactic medium, giving them the ability to retain cooler gas at temperatures that support its slow migration inward along potential gradients. The dark matter component determines the gravitational geometry, and the baryonic component reacts by falling into these channels and condensing wherever deeper gravitational valleys exist. The result is that galaxy-sized halos do not form in isolation, but instead grow near intersections of filaments, where convergence of matter is strongest. These nodes act as collection points, where gas accumulates, and where the seeds of large galaxies form and continue to grow. And this growth is not a single catastrophic collapse, but a long, steady process that continues while the filaments remain open supply routes. Some gas in these filaments remains diffuse and ionized, while some cools into denser clumps, and this combination ensures that at any given time there is both a reservoir that can stream inward and also structure within the reservoir that can be disturbed by passing gravitational encounters. When a small halo enters a larger halo, the orbits of its gas clouds are perturbed and torques can act to remove angular momentum, allowing the gas to sink deeper. Collisions between galaxies are common, and these events are not merely destructive but are highly efficient at forcing gas into the inner regions of the merger remnant. This behavior is a direct outcome of the large-scale environment, because the number of halos in a given volume is higher than at later times, and the typical separation between halos is smaller, increasing the rate at which interactions take place. The cosmic filaments feeding these regions remain rich, because star formation has not yet consumed most of the available matter, and the radiation fields from this region of the universe are strong, but not yet sufficient to strip every filament of neutral gas. In these circumstances, powerful active galactic nuclei ignite at the centers of the most massive halos because gas is constantly being pushed toward deeper, potential wells, not by any single mechanism, but by the cumulative effect of geometry and supply. In a high redshift environment like this, the concept of an isolated galaxy is not fully accurate, because every massive host sits at the intersection of networks that deliver mass. With steady supply available, it becomes possible for large black holes to grow continuously for extended periods. This environment also determines the densities of the circumgalactic medium, the gas that sits around the galaxy, and fills the region between the host and the intergalactic filaments. The circumgalactic medium can reach temperatures that inhibit cooling in some regions, while other zones remain cool and dense, and these different phases can coexist because the gravitational potential is deep enough to support hot gas, and the supply routes constantly replenish the cooler component. As matter flows inward, energy is transferred between components through shock fronts turbulence and radiative losses. Turbulent eddies form where substreams collide, and these eddies cascade energy down to small scales, where it is dissipated as heat or radiated away, and this process both heats and mixes the gas. Magnetic fields thread through the filaments and through the circumgalactic medium, and these fields are amplified where gas is compressed or stretched by shear flows. They are not uniform, and their intensity can vary across regions, but they can influence how charged particles move and how small-scale structures form within the bulk flow. Beneath these broad-scale phenomena, the deep potential wells of massive halos represent sinks into which gas continues to flow for extended periods, because the inflow does not finish quickly. Matter sinks slowly from the outskirts toward the central zones, because cooling time and dynamical time compete, and this slow inflow ensures that the supply to the central regions is not a single burst, but a long-sustained movement. As long as the filaments remain connected to the host region, gas continues to move inward. The rate at which this inward drift takes place depends on density, temperature, metallicity, ionization state, and the local gravitational curvature. In this environment, the fueling of massive nuclei is not an extreme exception, but a natural output of the distribution of cosmic matter. The quasar associated with TON 618 therefore must be considered as a phenomenon embedded in this larger geometry because its power is not produced in a vacuum, but is supported by inflow conditions that are set by these filaments and nodes. The energy it radiates is linked to how matter at very large scales is assembled and transported, and if these supply routes had been weak or intermittent, its radiative history would be very different. The outer environment, therefore, is not a passive background, but is an active and dynamic domain that sets the stage for continued supply. If these streams had been cut off or star formation had saturated the gas reservoirs, the massive nuclei at the centres of these young galaxies would have had much less to consume. The quasar epoch is defined in part by the fact that these conditions exist widely, so extremely bright active sources are a natural result of how the matter distribution behaves on scales of many millions of light years. The light that the quasar radiates originates in the inner region, but its fuel originates on scales so large that the full context must include the vast geometry of the cosmic web and the barriers and conduits that determine how the gas flows. The behavior of inflow and supply at this outer scale expresses itself in the statistical abundance of bright nuclei in this epoch, and is consistent with the large cosmological picture that dynamic filaments and high merger rates support ongoing fueling. The large-scale environment of TON 618 is thus a region in which gas is available, dynamic and continually directed inward by the structure of gravity and by the effects of interactions that constantly reshape orbits and bring new matter into regions where it can be compressed and cooled further. Within the broader cosmic web, each massive halo containing a forming galaxy sits not as a closed island but as a dynamic node immersed in a wider sea of inflowing matter, and in such nodes intense radiation emerges when the central mass switches on as an active nucleus. Because material arriving from large distances loses gravitational potential energy and converts that energy into heat and light in the inner zones. The region around the host of TON 618 is not quiet because the radiation from the bright nucleus escapes to distances that reach far into the surrounding medium, and this radiation interacts with gas in multiple ways. Ionizing photons can remove electrons from atoms and ions and change the thermodynamic balance of the medium, and this influences how gas cools and how turbulence decays. Radiation pressure can accelerate dust grains and influence the distribution of matter even at significant distances, because photons carry momentum, and when enough photons are present, the momentum transfer can alter gas trajectories. The host region of a hyperluminous quasar is therefore a multi-layered radiative domain, in which light and matter constantly exchange energy. Far from the centre, the light is diluted yet still strong enough to prevent gas from fully condensing into cold clouds, and this can reduce the rate at which gas forms stars in the immediate neighbourhood, because the gas may remain warm and ionized. In some directions, however, the medium may be shielded by dense clumps, and in those pockets gas can cool more effectively. This complex patchwork reflects the geometry of gas flows and the uneven distribution of density prior to illumination. In observational terms, the host region is not directly imaged in fine detail at this distance, because its angular size is too small, but statistical comparison with other known luminous quasars at similar redshift allows a consistent picture in which the interstellar medium and the circumgalactic medium remain strongly influenced by the intense radiative output. The luminosity is so high that the host region is flooded with ultraviolet light that originates from the hot accretion zone, and this light spreads outward into the ambient gas. When ultraviolet photons strike dust grains, the grains heat and re-radiate energy in infrared wavelengths that can escape more easily, because longer wavelengths are less likely to be scattered by small particles. The result is that the host region becomes an emitter not only of the direct light from the inner nucleus, but also of reprocessed infrared radiation. In many hyperluminous quasars at similar cosmic distances, the dust content in the host can be high enough to produce strong infrared spectral components. And this is consistent with the fact that even though heavy element abundance is lower than in the present era, generations of star formation have already occurred. Dust grains are made from heavy elements that stars produce, so the presence of dust in this environment confirms that star formation predates the ignition of the hyperluminous nucleus. When gas and dust in the host region are exposed to radiation, they encounter pressure gradients that can redirect their flows because radiation pressure can act as a force. Gas that is not strongly bound may be accelerated outward, and this can produce large-scale outflows. In some cases, these outflows may carry metals into the circumgalactic medium and contribute to enrichment. In other directions, gas may not be removed because the gravitational potential of the host halo is strong enough to resist such acceleration. These competing behaviors produce an anisotropic structure where different radial directions behave differently, and where the balance between inflow and outflow depends on density and temperature, and on the geometry of the gas. Host regions of bright quasars are therefore not uniform spheres, but irregular radiative ecosystems. Embedded within this complex environment, stellar populations continue to evolve, because star formation has already occurred before the nucleus became hyperluminous. Some stars form in dense molecular clouds that may have been present before the nucleus reached its present state, and some may form in shielded regions where radiation cannot penetrate deeply. The presence of these stellar populations ensures additional energy sources beyond the nucleus, because massive stars emit ultraviolet radiation, and supernova explosions return metals into the interstellar medium. Star formation may be regulated by the radiation from the nucleus, because intense light keeps some gas warm, while allowing other gas to remain cold only in shielded pockets. And this spatially dependent regulation introduces complex time-dependent feedback loops between AGN illumination and star formation efficiency. Observational evidence from similar systems suggests that quasar host regions in this epoch may contain both cold molecular gas and warm ionized gas in varying proportions, and this supports the idea that multiple temperature phases coexist. Each of these phases interacts differently with the radiation field. Warm ionized gas may flow outward more easily because thermal pressure and radiation pressure combine to produce winds. Cold dense gas may resist outward push because high density increases gravitational binding and self-shielding reduces ionization. These conditions produce the environment from which the inner fueling zone draws matter, because the gas that manages to shed angular momentum and remain gravitationally bound will eventually begin to sink inward through the host region, rather than remain trapped at larger radii. At the same time, the presence of strong radiation means that some material at intermediate radii may be prevented from cooling enough to join the inflow. This dual effect of feeding and regulating is a natural outcome of extreme luminosity. In such a host region, the interplay between supply and radiation is continuous, and the luminosity of the nucleus both depends on that supply and simultaneously responds to it. The observed brightness of TON 618 is a direct reflection of this connection, and the host region around it is an active boundary where energy and matter continually exchange momentum and thermal energy. The structure of the host region is therefore defined not only by the gravity of the central mass, but also by the radiative energy that floods outward at enormous power levels. Observationally, the host region cannot be spatially resolved at fine scales, but the energy budget implied by its luminosity requires an environment capable of sustaining inflow despite strong outward radiative influence. The existence of such an environment is consistent with the supply conditions of the quasar epoch, and the host region can be understood as a complex radiative domain that sits between the outer cosmic filaments and the inner accretion zones, and in this environment gas that can persist against radiation pressure will continue to sink deeper. The radiative power of a quasar is described by its luminosity, which is the total energy emitted per unit time across all wavelengths, and this quantity is not abstract, because it reflects the physical conversion of gravitational potential energy of infalling matter into light in the accretion structures near the central mass. In the case of extremely bright quasars in this cosmic era, the luminosity reaches values that are among the highest known because the mass inflow rates and the radiative efficiencies are sufficient to release energy at scales that are difficult to imagine in familiar stellar terms. Luminosity is not measured from a single waveband because the emission from the central engine spans wide portions of the spectrum from infrared, where dust re-radiates absorbed ultraviolet light, to ultraviolet, where the accretion region directly emits thermal and non-thermal radiation. For distant quasars such as the source associated with TON 618, the observed wavelengths are redshifted, and this means that instruments that operate in the optical band are sampling radiation that originally emerged from higher frequency bands. The underlying physical quantity, however, is the intrinsic luminosity, and this is determined by modelling the spectrum and accounting for the redshift. When these corrections are performed, the resulting luminosity values place this object among the most powerful radiative engines known in the universe that has been observed. The energy scale is not simply large in an intuitive sense, but can be quantitatively estimated in relation to a theoretical construct known as the Eddington luminosity, which is the energy output at which radiation pressure balances gravitational attraction for a given central mass. If a quasar radiates near this limit, inflow can be regulated by the outward force of light because photons carry momentum. The mass estimates for the black hole at the center of the quasar associated with TON 618 reach many tens of billions of solar masses, and this means that even the Eddington limit itself is enormous. The observed luminosity is a fraction of this limit, but the fraction is large enough that the system operates in a regime where radiation pressure interacts strongly with the surrounding medium. When luminosity increases, radiation pressure rises, and this can make it more difficult for gas to fall inward, because photons from the inner region push against it. When luminosity decreases, radiation pressure falls and inflow can become more efficient. In this sense, the central engine behaves as a feedback-regulated radiator, because the energy it releases affects the matter that sustains it. Luminosity cannot exceed the physical ability of the accretion structure to convert gravitational potential energy into radiation at an efficiency determined by the space-time geometry and radiative processes at small radii. If the mass of the central object is very large, the potential energy gradients near it are steep, and in falling matter releases a large amount of energy per unit mass. The high luminosity observed from this quasar implies not only a large inflow of matter, but also an accretion regime that operates at high efficiency. In astrophysics, the concept of bolometric luminosity is used to describe the total output integrated over all wavelengths, rather than a specific band. For extremely distant sources, the bolometric luminosity must be inferred from models, because only a portion of the spectrum is directly observable in a given instrument. These models are constrained by the shape of the observed spectrum and by the known redshift and by the comparison with other quasars of similar class. The extreme luminosity means that the environment around this system is saturated with radiation at intensity levels far beyond those in ordinary galaxies. This intensity influences the thermodynamics of the interstellar medium in the host region and the circumgalactic medium beyond it. The scale of the radiative power can be related to the mass accretion rate by multiplying the mass inflow by the efficiency of conversion of rest mass energy into radiation. Efficiency depends on the structure and dynamics of the inner region, but the luminosity constrains the product of efficiency and inflow rate. The fact that this object radiates at such high luminosity means that the inflow cannot be weak. The inflow must be sustained, because if inflow were to drop, the luminosity would drop as well. Observational surveys of bright quasars at similar redshift show that such high luminosity sources are rare but not unique. They populate the upper tail of the brightness distribution of active nuclei in the early universe. The extreme luminosity of the source associated with TON 618 confirms that the mass supply environment is strong enough to feed the central engine at rates that are persistently high. The radiation produced by this engine escapes through paths that may be anisotropic because gas distribution and dust opacity are not uniform in all directions. Even when anisotropy is considered, the total power output remains enormous. This radiative power changes the ionization structure of the region around the nucleus because photons ionize gas, and this produces emission lines that can be used to diagnose the physical properties of the gas. Broad emission lines are observed because the gas near the nucleus moves at high velocity. The strength of these lines depends in part on the ionizing luminosity. When luminosity increases, more atoms are ionized, and the line emission can become stronger. When luminosity decreases, the ionization parameter changes and emission may weaken. In this sense, luminosity acts as a driver of spectral behavior. The physical implications of such extreme radiative power extend to the heating of gas on kiloparsec scales. Dust grains absorb ultraviolet radiation and re-radiate in the infrared, and this infrared emission contributes to the energy budget of the host region. The luminosity also heats the electrons in ionized gas and influences thermal stability. The process of illumination by such a bright source therefore not only arises from accretion, but also shapes the physical state of the region from which the matter originates. The measurement of luminosity for this source reflects a combination of direct observation modeling and comparison to other known luminous quasars. The resulting estimates are consistent with the picture that the quasar associated with TON 618 radiates with intensity high enough to influence its surroundings on scales that exceed the inner accretion region by large factors. The radiative power of this quasar is thus an intrinsic physical property that arises from accretion and that defines the environment in which it resides. It is not an incidental feature but is the direct measurable expression of the energy conversion that takes place in the central zones, where gravitational potential energy becomes heat and light. Relativistic jets associated with bright quasars extend far beyond the inner regions that directly surround the accretion flow and reach intergalactic scales where they inject energy and momentum into the medium over distances that can span hundreds of thousands of light years depending on the density of the environment and the magnetic field configuration along the trajectory. These jets are made of charged particles accelerated to speeds close to the speed of light, and because these particles are relativistic, they radiate synchrotron emission when they spiral around magnetic field lines. This emission can appear at radio wavelengths, and in some cases at higher energies depending on particle populations and field strengths. The significance of such jets in the context of a quasar that is as luminous as the one associated with TON 618 is that they represent a channel through which power is transported out of the central region. The energy carried by the jets is not free in the sense that it originates from accretion and from the magnetic and dynamical extraction of energy from the inner flow. Once launched, the jets propagate outward and interact with the environment in ways that depend on density gradients and magnetic topology. If the medium is dense, the jets may slow and deposit energy locally. If the medium is thin, the jets can travel larger distances with less dissipation. In either case, the jets do not merely pass through the universe like isolated beams. They interact with gas shock it heat it, and in many cases displace it. On large scales, the jets carve channels or cavities in the intergalactic medium, and these cavities can remain present long after the jet activity is weakened. In radio images of some bright quasars and radio galaxies, these cavities appear as large, diffuse lobes. The existence of such lobes demonstrates that energy has been delivered to these large distances, because the lobes are filled with plasma that has been energized by the jets. The geometry of the jets is influenced by the magnetic field configuration in the inner region, but once they propagate far outward, they are subject to bending or disruption by pressure gradients or turbulence in the medium they traverse. In the high redshift universe, where the quasar associated with TON 618 emerges, the intergalactic medium is denser than in the present universe, and this means that jet interactions can be more efficient at transferring energy into ambient gas. The momentum carried by the jets can compress gas, and in some cases accelerate it outward. This acceleration can influence structure formation, because gas that is heated or displaced by the jets may become less able to fall inward toward the central regions of the host. The jets can thus regulate the supply of cold gas to the host galaxy, and this effect is part of what is known in broader astrophysical language as feedback. In addition to the dynamical interactions, jets emit radiation across the electromagnetic spectrum, and this emission can be observed as radio emission, or in some cases as optical or X-ray synchrotron emission, depending on particle populations. The amount of energy in the jet relative to the radiative luminosity of the quasar depends on the specific properties of the system. In some sources, jets carry a large portion of the total power. In others, jets are present but are less dominant relative to radiative output. For an ultraluminous quasar associated with a black hole mass in the tens of billions of solar masses range, it is expected that the jets, if present, would be capable of transporting very large energy fluxes. Observations of similar luminous quasars show that some have strong jets and some do not, and this diversity reflects differences in the spin of the central object, the geometry of the magnetic field, and the structure of the inner accretion flow. When jets are present, they can be seen at large distances because their radiation is concentrated along a narrow direction due to relativistic beaming. If the jet is pointed close to the line of sight of the observer, the emission can appear particularly bright. The jet phenomenon therefore has both dynamical effects on the environment and observational effects on the way the quasar is detected. In the context of extreme quasar environments like that of TON 618, the existence of large-scale jets would imply that energy is being transported far beyond the region in which the radiation from the accretion disk directly dominates. It would imply that the influence of the central engine is not limited to local heating or ionization near the core, but instead reaches deep into intergalactic space. Jets also influence magnetic fields because the motion of charged particles within the jet amplifies and stretches magnetic field lines. This magnetization can persist after the jet event ends and may influence the field structure of the intergalactic medium. In addition to carrying momentum, jets carry energy in the form of relativistic particle populations and magnetic fields. The particle populations inside jets can contribute to cosmic ray populations. Although much of the jet power is eventually dissipated in interactions with the intergalactic medium, the initial propagation of the jet remains a direct signature of the central engine that launched it. When jets reach large distances, they can also produce hotspots, where they encounter dense clouds and shock them. These hotspots are regions where energy is deposited rapidly. The presence of such hotspots demonstrates that jets can remain coherent over very large distances. Even in cases where jets do not remain collimated, they leave behind traces of past activity in the form of extended lobes and diffuse radio structures. The impact of jets thus remains long after the central engine changes its output level. On cosmic scales, jets contribute to the mixing of energy between galaxies and their environments. They help to transport metals into the intergalactic medium because they can entrain some mass along their propagation path. They shape the thermodynamic state of gas in clusters by injecting heat and preventing excessive cooling. In the early universe, these effects are particularly relevant because the high densities and high supply rates mean that jet interactions may exert significant control over gas flows. Jets represent a vector by which gravitational energy originally associated with inflowing matter is redistributed into the outer environment in the form of kinetic and magnetic energy. The extreme luminosity of this quasar indicates strong inner activity, and jets, if present, would act as extended expressions of that activity. Their presence would confirm that the influence of the central engine reaches far out into the environment. The full physical significance of jets on intergalactic scales is that they connect the tiny inner region, where matter becomes radiation, and relativistic plasma to domains that span scales many orders of magnitude larger. Their existence in such systems therefore demonstrates that the consequences of gravitational energy released near a central mass do not remain confined, but instead propagate into the wider universe and imprint measurable structure into the space between galaxies. Radiation interacts with matter not only by heating it, or by changing its ionization state, but also by exerting force, because photons carry momentum, and this momentum can be transferred to atoms, ions, electrons, and dust grains when light is absorbed or scattered. In an environment where luminosity is modest, this force may be small compared to gravity or thermal motion, but in a quasar environment as bright as the one associated with the black hole, in TON 618, the momentum carried by light is large enough to shape the structure and motion of gas across extended regions. Radiation pressure works by pushing outward on any material that can couple with photons. When photons strike dust grains, the momentum transfer can accelerate those grains, and gas that adheres to dust through collisions or through electrostatic forces can be dragged outward as well. This produces a radiative wind that can remove matter from regions where gravity alone would otherwise hold it. The efficiency of this momentum coupling depends on the opacity of the material, because opacity determines how strongly photons interact with it. Dust is highly opaque in the ultraviolet and optical bands, and therefore dust is particularly sensitive to radiation pressure in these wavelengths. Gas that is ionized can also interact with photons through scattering, especially through electron scattering, and this interaction can also transfer momentum. In the context of a hyperluminous quasar, the density of photons emerging from the inner accretion region creates a radiation field that is intense enough to push against gas and dust, not only in the immediate surrounding environment, but also across distances that reach into the host galaxy and into the circumgalactic medium. Radiation pressure therefore becomes one of the fundamental regulators of inflow, because inflow requires that matter maintain inward-directed momentum. If radiation pressure grows strong enough in a given direction, matter in that direction may be slowed or reversed. The behavior that results from this outward-directed push is not uniform, because the density and opacity of gas and dust is not uniform. Some regions around the nucleus may be thick with dust, and these regions absorb more photons and re-radiate energy in the infrared. Other regions may be dust poor and allow photons to pass more easily. This geometric and compositional diversity creates anisotropic radiation pressure fields. In some directions, gas may be driven outward, and in others gas may still fall inward despite the luminous push. The existence of these multi-directional patterns means that the gas in the region responds to radiation not as a uniform outward shell, but as an irregular network of flows. Some flows are outward, some are stalled, and some continue to sink inward. The intensity of radiation from the nucleus changes with accretion rate. When the central engine is in a high state, the radiation field becomes stronger, and the outward push becomes more effective. When the central engine is in a lower state, the radiation field weakens, and the matter in the environment becomes more free to move inward. These changes produce a dynamical equilibrium between the accretion flow and the radiation field, because mass supply and mass removal occur simultaneously at different radii. Radiation heats gas to high temperatures because photoionization adds energy to electrons, and this energy is then shared among particles through collisions. As gas heats, it expands, and expansion itself produces pressure that can counteract gravity. Radiation therefore stabilizes some gas against collapse simply by keeping it hot. In the case of dust grains, heating may cause sublimation near the central region, where temperatures reach values that are too high for solid grains to survive. Dust grains can only persist beyond a certain radius where temperature remains below destruction thresholds. Inside this sublimation radius, dust no longer exists, and photons therefore interact more strongly with electrons through scattering rather than absorption by grains. The effective coupling mechanism therefore varies with radius. In regions closer to the nucleus, electron scattering dominates, and in regions farther away, dust absorption dominates. This variation creates layers of momentum coupling strength, each dependent on the local opacity. The feedback imposed by radiation pressure not only affects inflow, but also influences star formation, because star formation requires cold, dense gas that can collapse under gravity. If radiation keeps gas warm and ionized, then that gas will be unable to collapse into stars. Observational studies of luminous quasars at similar redshift indicate that radiation may suppress star formation in the inner regions of the host domain, because energy input from the nucleus prevents gas from cooling. The existence of star-forming regions at larger distances where shielding is more effective suggests that radiation pressure and radiative heating operate more strongly near the nucleus than at outer radii. The pressure exerted by the radiation field also influences dust transport, because dust grains are accelerated outward and can travel large distances before slowing down, and in doing so, dust can be distributed in structures that trace the radiation field. If these grains carry elements produced in earlier generations of stars, then the radiation field effectively transports these elements outward. In the context of the quasar associated with TON 618, the intensity of radiation is strong enough that dust distribution becomes biased toward directions of lower optical depth. These directional differences produce observational asymmetries that can be detected through differences in spectral slopes or polarization signatures in different lines of sight. Radiation pressure also influences the geometry of ionization fronts, because regions that receive direct illumination become fully ionized while regions behind thick clouds remain neutral or only partially ionized. Ionization fronts shape the boundaries between different thermal phases and determine where recombination emission occurs. Radiation pressure can shift these fronts outward or inward depending on luminosity. The consequence of these processes is that the region surrounding the bright nucleus becomes a dynamically evolving medium in which gas, dust, and radiation remain in continuous interaction. The radiation that escapes from the accretion zone is not simply an endpoint of energy conversion, but is a controlling agent that modifies the structure and motion of the matter that originally fuels the engine. In very luminous quasars, radiation pressure thus becomes not merely a passive property, but an active structural force that helps to define how material is arranged in the host region and how that material evolves with time. At larger radii from the host, where the radiation field has weakened enough to allow the gas to approach a roughly quasi-static state. Without immediate catastrophic outward acceleration, the supply reservoir remains the vast circumgalactic and interstellar medium that has been shaped by earlier gravitational assembly and merger-driven mass transport, because this material, although partially heated and partially ionized, is still bound to the potential of the host halo and still represents the stores from which the accretion process can draw. This reservoir is not a single smooth cloud, but a complex mixture of gas phases that coexist simultaneously. Some regions are warm and ionized, where photoionization and cosmic shocks have deposited heat. Other regions are cooler and more neutral because they are shielded from direct illumination. Some material exists in denser clumps that may still carry molecular content, and these clumps, even in a high luminosity quasar environment, can act as compact pockets of potential inflow fuel if they manage to survive tidal shear and disruptive feedback processes. The presence of this reservoir is consistent with the fact that the quasar epoch has high gas supply in the cosmic filaments, and that galaxies in this epoch remain deeply embedded in a web of cold and warm matter. The reservoir is not a static container. It evolves as material is added from mergers, as it is removed by star formation, as it is heated by radiation from the nucleus, and as it is stirred by turbulence. Turbulence arises because gravitational interactions, shocks, and non-uniform radiation fields generate velocity fluctuations at multiple scales, and these fluctuations cascade energy to smaller eddies until dissipation converts some of this turbulent motion into heat. The turbulent spectrum implies that different parts of the reservoir have different densities and velocities, and this diversity plays a crucial role in determining which parcels of gas can eventually move inward. The reservoir holds the material that eventually will become part of the accretion flow, but not all material in the reservoir will end up in the central region. Some gas will remain in orbit around the host, some will be removed by radiation pressure or mechanical outflows, some will form stars if it cools sufficiently. Only a fraction will lose enough angular momentum to spiral inward. Angular momentum is a key constraint because mere gravitational binding is not sufficient to guarantee inflow. Matter in orbit around a massive halo possesses angular momentum that prevents direct radial collapse. To move inward, angular momentum must be transferred outward to other material. This transfer can occur through gravitational torques, when galaxy-scale encounters disrupt stable orbits, or through magnetic stresses in ionized gas that allow angular momentum to be redistributed. It can also occur through cloud-cloud interactions in which collisions exchange momentum and energy and leave behind a fraction of gas with lower angular momentum. As gas loses angular momentum, it begins to sink deeper into the gravitational well. At some point, the inflow transitions from being a largely chaotic cloud-dominated motion to a more coherent inward stream. This transition does not have a single sharp boundary, but represents a gradual shift from turbulence-dominated flow to rotation-dominated flow near the central region. The density in the reservoir is high enough that self-gravity can play a role in shaping the clumps. Clumps that become dense enough may cool faster than their surroundings, and this local cooling allows them to contract further. If radiation from the nucleus is not too intense in a given direction, a cloud may survive intact long enough to reach smaller radii. If radiation is strong enough, it may destroy the cloud or strip its outer layers. This competition between cooling collapse and radiative destruction produces an environment where only some clouds succeed in travelling inward. The formation of stars within this reservoir depends on whether cooling is sufficiently rapid for collapse to occur before radiative or mechanical feedback disrupts the cloud. In many quasar host systems, star formation still takes place in the outer reservoir because shielding from dust and geometry can allow some regions to remain cold enough for molecular gas to form and persist. This star formation soon returns metals to the reservoir through supernova explosions, and these metals enhance cooling. Metal-enriched gas cools more efficiently than pure hydrogen gas. Enhanced cooling increases the chances that some material will condense into clouds that can eventually move inward. The reservoir is therefore self-modifying because star formation and feedback can produce conditions that both encourage and hinder subsequent inflow. Meanwhile, the gravitational structure of the halo remains the deep well that keeps most of this material gravitationally bound. Even though radiation pressure may accelerate some gas outward, the escape of that gas depends on whether the outward push exceeds escape velocity. In directions where radiation pressure is not strong enough to overcome gravity, gas remains confined. Gravity thus remains the final arbiter of whether gas stays near the system. The reservoir is vast in spatial extent compared to the inner accretion disk. It is the place where matter resides before any disk-like structure forms. The reservoir is an outer holding domain wherein matter may remain for long periods before any transformation into a disk occurs. At this scale, the matter is closer to the halo scale rather than the nuclear scale. It is this reservoir that supplies the intermediate region that eventually transitions into a rotational inflow. Without this large outer storage domain, the engine at the center could not sustain extreme luminosity for long. The radiative power that emerges from the nucleus is tied to the rate at which mass passes through the disk. The disk cannot remain luminous unless the reservoir continues to deliver material. In the quasar epoch, when such reservoirs are common and rich, luminous active nuclei therefore often reach very bright states. The inflow from this reservoir toward the central regions is a gradual process that can take millions of years, as material slowly sheds angular momentum. During that time, the reservoir continues to experience radiative heating and mechanical shaping by outflows and jets. The complexity of this domain is a direct expression of the multiphase nature of gas, the presence of dust, the influence of turbulence, and the fact that the cosmic epoch still supplies gas from the outside. The extreme power of the nucleus is ultimately an inward conversion of gravitational energy, but that process begins here far from the central disk in the extended reservoir that holds the matter that has not yet become part of the rotating flow. As gas moves inward from the reservoir and the cloud-dominated dynamics slowly give way to increasingly organized orbital motion, the material that survives radiative disruption and mechanical stripping eventually settles into a configuration in which rotation becomes the dominant structural property, and shear forces begin to redistribute angular momentum in a coherent manner that marks the formation of an accretion disk, a flattened rotating flow in which matter orbits the central mass on trajectories that lie roughly in a plane, defined by the net angular momentum of the inflowing material. This disk does not form instantly, because the gas that arrives from larger radii is not initially in circular orbit. It arrives with a mixture of velocities and directions, but as turbulence decays and collisions among gas parcels exchange momentum, the net residual motion becomes planar. Collisions and magnetic stresses remove angular momentum from matter that seeks to move inward, and this angular momentum is carried outward by other material that moves away, or by waves that propagate through the disk. The process of angular momentum transport is essential because without it the gas would remain in almost circular orbits and never reach the radii at which gravitational potential energy can be efficiently converted to heat and radiation. In a disk, the kinetic energy of orbital motion is slightly less than the potential energy released as the matter spirals inward. The difference is dissipated as thermal energy. Where radiation is efficient, this thermal energy is emitted as photons. This disk, therefore, becomes the primary interface between gravitational energy and electromagnetic output. Even at moderate radii, the temperatures achieved can be high. In extremely luminous quasars with very large central masses, the radii at which the disk becomes hot enough to emit ultraviolet light may be larger than in less massive systems, because the gravitational potential has a shallow curvature at very large distances, and only closer to the center does the energy change per radial interval become large. The disk is not a simple laminar flow. It has vertical structure because thermal pressure supports gas above the midplane. The disk is not infinitely thin. It has thickness determined by temperature and by radiation pressure. In regimes where the radiation pressure becomes larger than gas pressure, the vertical structure is supported not mainly by thermal motion, but by the outward momentum of photons. In high luminosity quasars, the innermost zones of the disk may reach these radiation pressure-dominated states. The disk is subject to instabilities because the balance between heating and cooling can change with radius. If a portion of the disk becomes too hot, it may puff up and increase its vertical thickness. If it cools too much, it may thin. The energy generated by viscous dissipation must be radiated away for the disk to remain stable. The efficiency with which radiation escapes depends on opacity. If the disk becomes too opaque, radiation may be trapped, and the disk region may expand. These behaviors influence the vertical structure over time, but even with these complexities, the disk remains the engine of conversion in luminous quasars. In the case of the quasar associated with TON 618, the disk must sustain mass accretion at extremely high rates, because the radiative power is so large that the required mass inflow must be correspondingly large when multiplied by radiative efficiency. The temperature gradient in the disk increases inward because gravitational potential energy depends on radial position. The region farther out is cooler and emits more in optical or near ultraviolet when redshift is removed. Closer in the disk becomes much hotter and emits in ultraviolet or extreme ultraviolet, before redshift shifts these wavelengths into observed optical or near-infrared bands. The disk rotates differentially, which means orbital period depends on radius. The inner regions orbit faster, and the outer regions orbit more slowly. This differential rotation stretches magnetic field lines and generates shear that can drive turbulence. The magnetorotational instability is believed to be one of the primary mechanisms by which angular momentum is transported in the disk. This instability arises from the interaction of magnetic fields with differential rotation. Charged particles tied to magnetic field lines experience forces that link different radial annuli, allowing angular momentum to be exchanged across radius. The result is that inner gas can move inward while outer gas can move outward. The inner inflow continues until it reaches radii, where the conversion of gravitational potential energy to radiation becomes extremely efficient. At the densities and temperatures found in such disks, the ionization fraction is high, and magnetic fields are dynamically important. The luminosity that emerges from the accretion disk of such a massive system is directly tied to how much gravitational energy is released per unit mass, and how effectively that energy is radiated. The disk is not static, because the accretion rate changes with time depending on how efficiently the outer reservoir delivers material. If the supply weakens, the disk emission decreases. If the supply strengthens, the disk emission increases. The disk therefore behaves as a quasi-steady flow that reflects the balance between inflow and radiation. Thermal equilibrium in the disk is not trivial because heating by viscous dissipation competes with radiative cooling. If cooling is insufficient, then thermal energy builds up and vertical expansion can occur. These properties define the thermal and radiative structure of the disk. In the context of a system with mass measured in tens of billions of solar masses, the disk must extend across large radial distances because the gravitational radius is large. The inner disk is extremely hot and may reach temperatures at which ionization is complete. The outer disk may be cooler and may contain partially ionized gas. But regardless of these variations, the disk serves as the region in which the transition from reservoir gas to radiative energy occurs. Each parcel of gas that reaches the disk has lost angular momentum through interactions outside and inside the disk. Once in the disk, the parcel continues to spiral inward, shedding angular momentum until it arrives near radii, where gravitational energy release is maximal. In this region, the power that eventually appears as quasar luminosity is generated. The disk marks the point where cosmological matter flows halo-scale turbulence, radiation modulated inflow and magnetic stresses converge to create an engine that transforms potential energy into radiation. The temperature inside the accretion disk is not uniform because gravitational potential energy release depends on radius, and this energy release produces gradients in thermal conditions as matter moves inward on circularizing orbits, which steadily become tighter as angular momentum is transported outward. At large radii, the disk is cooler because the amount of gravitational potential energy that can be liberated per unit mass is smaller, and the orbital velocities are lower. As the disk gets closer to the central mass, the orbital velocities increase, and the change in energy per radial interval becomes steeper, so the dissipation per unit volume becomes greater. This creates a radial temperature profile in which temperature rises sharply toward the inside. The magnitude of the temperature depends on radiative efficiency, the composition of the gas, the ionization fraction, and the opacity of the material. Hydrogen and helium dominate the composition, but heavier elements still exist in non-zero abundance, because earlier stellar generations have enriched the gas. These heavy elements provide additional opacity in ultraviolet bands and help determine how radiation escapes from the disk. At the high accretion rates associated with extremely luminous quasars, the disk can reach temperatures in the inner regions that produce photons in the ultraviolet, and even the extreme ultraviolet when rest frame emission is considered prior to redshift effects. Radiation that originates from these temperatures will appear at longer wavelengths when observed, because cosmological expansion stretches the light. The shape of the disk spectrum reflects the thermal distribution across the disk. Different radial zones emit different parts of the spectrum. When this emission is integrated across the entire structure, it forms a multicolor blackbody spectrum in which each annulus contributes a different thermal component. Radiative transfer within the disk determines the efficiency at which heat can escape as photons. The opacity of the gas is dominated at some radii by electron scattering, and at other radii by bound-bound transitions in metals. In the inner disk, where temperatures are so high that atoms become fully ionized, electron scattering becomes the dominant opacity source. The photons emitted in this region scatter multiple times before escaping, and this scattering shapes the emergent spectrum. In the outer disk, where temperatures are lower, heavy element lines contribute to opacity, and molecular species may form if the temperature is low enough. However, in an extremely luminous quasar environment associated with a central mass measured in many tens of billions of solar masses, the inner disk extends farther out than in less massive systems, and the boundary between fully ionized and partially ionized zones may be shifted outward. In such systems, the spectral energy distribution contains substantial ultraviolet power, because the temperature gradient provides large radiative contributions from hot inner regions. The disk thickness is also influenced by temperature because thermal pressure and radiation pressure support material vertically. If radiation pressure dominates the disk, can inflate vertically into a thickened configuration. If gas pressure dominates, the disk remains thinner. The ratio of these two pressures depends on radius. Closer to the central engine, the radiation pressure increases because luminosity is generated there. In some models, the innermost disk may be radiation pressure dominated over extended radial zones. These zones may be subject to instabilities that produce fluctuations on timescales, determined by thermal and viscous times. The emission from the disk is generated by viscous dissipation that converts orbital energy into heat. This heat is then radiated away by photons. The temperature of the disk at each radius must satisfy the energy balance between heating and cooling. If heating exceeds cooling, the disk temperature rises until radiative losses increase. If cooling exceeds heating, the disk temperature decreases until heating catches up. This thermal coupling regulates the temperature structure. Observationally, the broad shape of the quasar spectrum indicates that the disk emission in extremely luminous quasars like this one must originate in a region where temperatures reach many tens of thousands of degrees Celsius or more. In the extreme inner radii, temperatures may rise still higher. The radial temperature gradient is steep and can be described by relationships that depend on mass accretion rate and mass of the central object. For a given mass accretion rate, a larger central mass produces a cooler disk at a given gravitational radius, because the gravitational potential gradient is shallower in physical units, farther from the event horizon. However, because extremely massive black holes can sustain large accretion rates, the luminosity remains extremely high even when the temperatures at a given fraction of the gravitational radius are lower than in systems with smaller mass. In an extremely massive system, these competing scalings combine to produce disks that can remain luminous across much larger physical sizes. This is one reason extremely massive quasars remain detectable across enormous distances, because their luminous surfaces cover larger areas when converted into physical units. The radial temperature structure matters because it determines which atomic transitions can occur in the disk atmosphere and which photons can escape. The disk atmosphere is the uppermost layer of gas that sits at the interface between the opaque photosphere and the lower density corona above it. Temperature determines the ionization state of this atmosphere. In hot regions, atoms are fully stripped, and the atmosphere contains mostly free electrons and atomic nuclei. In cooler zones, some electrons remain bound and line opacities emerge. These opacities influence radiative transfer and shape spectral features. The temperature gradient, therefore, is fundamental to the disk's ability to radiate energy. Without this gradient, the disk would not produce the multicolor spectral distribution characteristic of bright quasars. The energy radiated from the disk sets the energy scale for all radiative processes outside the disk. The luminosity associated with the disk influences the radiation pressure at larger radii. The spectral shape influences ionization in the surrounding gas. The disk temperature structure thus determines how the surrounding environment responds to radiation and how feedback proceeds. The central disk is the source of the photons that heat the surrounding medium. The gradient in disk temperature also determines how far into ultraviolet bands the spectrum extends before redshift shifts those photons into lower frequency bands. These thermal facts are inseparable from the observed brightness of the quasar associated with TON 618 because they represent the direct physical connection between accretion and emission. In the inner disk, the temperature continues to rise as radius decreases until the flow approaches radii where orbital energy release becomes so extreme that additional structural changes in the plasma and radiation environment become relevant. Above the hot photosphere of the disk, there exists a region known as the corona, which consists of a population of energetic electrons suspended in a tenuous and magnetically influenced layer, where temperature reaches values far in excess of the disk beneath it. Because the mechanisms that heat this gas deposit energy in a way that cannot be removed through purely thermal radiation at the same rate that energy is supplied. The corona is not a solid layer in any mechanical sense, but a volume in which charged particles interact with magnetic fields and radiative photons in a non-equilibrium plasma environment where electron temperatures can reach values so high that the electrons are thermalized at energies far greater than the characteristic thermal energy of the disk atmosphere. The exact heating mechanism is not fully determined, but in many theoretical models, magnetic reconnection plays a major role because differential rotation inside the disk stretches magnetic field lines until they become unstable and reconnect in short impulsive events that release magnetic energy directly into the particle population. When reconnection occurs, magnetic field topology changes and stored magnetic energy becomes particle energy. These particles lose energy through various radiative channels, and one of the most important of these channels is inverse Compton's scattering, in which electrons transfer energy to lower energy photons by scattering them to higher frequencies. This process increases the energy of photons that originate in the disk, because photons that leave the hot surface of the disk with energies corresponding to ultraviolet wavelengths can be upscattered into X-ray wavelengths after collisions with the hot electrons in the corona. The spectrum of the corona therefore reflects a combination of thermal Comptonization and non-thermal interactions, because electrons do not necessarily share a single temperature. The emergent spectrum in many luminous active nuclei contains a significant X-ray component that originates from this Comptonization process. The strength of this component depends on the optical depth of the corona and on the temperature distribution of the electrons. If the corona has high optical depth, photons may scatter many times before escaping, and this can create a power law spectrum that extends over large frequency ranges. If the corona has low optical depth, photons scatter fewer times, and the energy distribution may be more strongly shaped by the hottest electron populations. In the context of a hyperluminous quasar such as the one associated with the black hole in TON 618, the corona must be heated at a rate that is sufficient to sustain a high level of Comptonization, because the observational signatures of bright quasars of this class show strong high-energy continuum components that cannot arise from the disk alone. The disk emits thermal radiation that peaks in ultraviolet bands when expressed in the rest frame of the emitter, but the X-ray continuum arises from scattering. The presence of this corona therefore adds an entire additional layer of energy conversion, because photons that would otherwise escape at lower energy are upgraded to higher energy channels. Magnetic fields play a central role because the magnetorotational instability that drives angular momentum transport also feeds the build-up and configuration of magnetic structure in the disk atmosphere. Field lines that emerge from the surface of the disk can form loops above the disk, and these loops may reconnect when differential rotation twists them. When reconnection releases energy into electron populations, the electrons reach extremely high kinetic energies, and those electrons then upscatter photons. The coronal plasma may also launch outflows because strong magnetic pressure at small radii can accelerate particles along open field lines. These outflows can contribute to winds, which then transfer energy mechanically to gas at larger radii. The corona therefore influences both radiative and mechanical energy channels. The efficiency of Compton scattering depends on the relative energies of electrons and photons. When electrons have much higher energy than photons, the scattering is in the Thomson or Klein-Nishina regime depending on the energy scale. At energies relevant for X-ray production, the scattering can modify the photon energy by factors of many. The scattering process redistributes photon energy, but the total number of photons is approximately conserved. The net result is a high-energy tail in the emergent spectrum. Observationally, this tail is a signature of a corona that is energetic and extensive. The existence of such a corona in extremely massive quasars is consistent with the theoretical requirement that energy extraction must not simply end at the thermal disk, but must include channels that channel energy into high-energy radiation as well. The corona may not have a sharp boundary, but transitions gradually from the disk atmosphere into the outflow region above the disk. The ionization state in the corona is complete, because temperatures are so high that electrons no longer remain bound to nuclei. The material is transparent to many photons because the density is low, but is not transparent to scattering, because free electrons still interact strongly through Thomson scattering. The corona thus sits as a scattering layer above the disk that modifies outgoing photons. The balance between heating and cooling in this region determines how the corona maintains itself. Heating comes from reconnection and other magnetic dissipation processes. Cooling comes from inverse Compton scattering, because electrons lose kinetic energy when they transfer that energy to photons. The energy budget of the corona therefore must satisfy a non-thermal balance in which heating matches cooling. When heating increases more, Comptonization occurs and the X-ray continuum strengthens. When heating decreases, the corona cools and the X-ray continuum weakens. This dynamic coupling links magnetic field evolution to spectral shape. In the case of extremely luminous quasars with large central masses, the corona may extend over broad radial regions because the surface area of the disk is large when measured in physical units. The total energy contained in the corona may be substantial because the volume is large and the electron population is hot. The existence of a corona above the disk therefore represents an extension of the accretion structure into a region where electromagnetic interactions dominate the energy exchange. The corona sits above the photosphere of the disk and acts as an intermediary layer in which radiation from the disk is modified before escaping into space. Each photon that leaves the disk may pass through this region and have its energy altered by scattering. The high-energy photons that emerge from this region influence ionization states in gas that sits beyond the immediate disk environment. The corona therefore plays a direct role in determining how the outer environment responds to the central engine, because it supplies a portion of the photon distribution that controls the ionization parameter in gas clouds located at larger radii. Farther outward than the inner corona, yet still well within the gravitational dominance of the central mass, lies a region filled with dense clouds of ionized gas that orbit at high velocity and that produce spectral lines broadened by Doppler shifts because their orbital speeds reach many thousands of kilometers per second when expressed in rest frame units prior to cosmological redshift. This region is called the broad line region, and it is not a thin continuous shell, but rather a three-dimensional distribution of clumps whose density is high enough that ionization and recombination take place at rates sufficient to produce strong emission lines across ultraviolet and optical wavelengths. These clouds are not cold neutral clouds like molecular reservoirs, but instead are ionized and hot because the radiation from the central disk and the corona fills this region with photons that maintain high ionization fractions. When atoms in these clouds capture electrons, the electrons cascade down energy levels and emit photons with characteristic wavelengths. Because the volumetric density of clouds is high, and because the velocities are large, the resulting lines appear broad when observed. The degree of broadening depends on velocity. Larger velocities produce larger Doppler spreads. The clouds do not orbit in synchronous rigid motion, but instead move on different orbits with different radii and different inclinations relative to any given disk plane. Observed line widths therefore reflect the ensemble of velocities rather than a single coherent motion. The broad line region is also not homogeneous in density. Some clouds are denser and some are less dense. The ionization parameter, which describes the ratio of ionizing photon flux to particle density, determines how ionized each cloud becomes. Clouds closer to the center receive stronger radiation and may reach higher ionization states. Clouds farther away receive weaker radiation and may show lower ionization or different line strengths. These differences produce a range of spectral features in emission. The chemical composition of these clouds reflects the abundances from which they formed, but because star formation and enrichment have already occurred in the host system, these clouds contain heavy elements. Heavy element lines such as carbon, nitrogen, and oxygen appear strongly in quasar spectra. The presence of these lines indicates that the broad line region contains gas enriched by prior stellar generations. The gas in this region has been subjected to shear and turbulence and has been irradiated by ultraviolet and X-ray photons. As a result, the ionization state is dynamic. Photoionization dominates the upper layers of each cloud, and recombination dominates the deeper layers. Radiation can penetrate some depth before absorption. The depth depends on density and on composition. The clouds are large enough that radiation does not instantly destroy them, but not so large that they can avoid being altered by photon interactions. The thermal conditions in this region depend on the balance between photoionization heating and radiative cooling. Cooling occurs through line emission when ions recombine, or when electrons transition between energy levels. Heating occurs when photons ionize atoms. The equilibrium temperature that results is high enough that gas remains ionized. The density is high enough that collisional processes occur frequently. These collisions redistribute energy between particles and allow the gas to approach thermal equilibrium at a temperature appropriate to its ionization state. The orbital speeds of the clouds are gravitationally determined and decrease outward according to the mass of the central engine and the radius at which the clouds orbit. Because the central mass in this system is extremely large, the gravitational potential well is deep, and clouds remain bound even at high speeds. Observations of broad line widths can be used to estimate the mass of the central object, because velocity dispersion reflects gravitational binding. In quasars with mass measured in many tens of billions of solar masses, the broad line region velocities must be correspondingly large because the gravitational influence of such a massive central engine extends farther outward in physical units than in systems of smaller mass. This means that the characteristic radii of the broad line region may be larger in physical size while still reflecting strong velocity fields. Broadline gas in such an environment thus occupies a region whose physical extent is large, but whose gravitational curvature remains steep. The region is illuminated from the inside. The radiation that reaches this domain includes the thermal ultraviolet emission from the disk and the X-ray continuum produced by the corona. Both types of photons affect these clouds. X-ray photons penetrate deeper into the cloud structure and can alter ionization at depths not reached by ultraviolet photons. This interplay between ultraviolet and X-ray ionization creates stratified ionization layers within each cloud. The location of these layers depends on density. Denser regions self-shield more effectively. lower density regions become more fully ionized. The distribution of these layers influences which emission lines are strong in the emergent spectrum. In this region, the gas is not static. Radiation pressure can alter cloud trajectories slightly, especially for lower mass clouds. Collisions between clouds can occur when orbits intersect. When collisions occur, clouds may merge or fragment. Fragmentation can produce smaller clumps with new density distributions. These clumps may then respond differently to ionizing photons. Gas may evaporate from the cloud surfaces under strong illumination. This evaporated gas may form a kind of atmosphere around each cloud. That atmosphere may be photoionized and contribute to the observed emission. The presence of outflow may affect the broad line region, because outflowing gas may intersect the region and modify density distribution. In many luminous systems, emission profiles show asymmetries that may reflect bulk flows or anisotropic illumination. In the environment relevant to a hyperluminous quasar associated with such a massive central object, the broad line region must exist in a state of continuous equilibrium between gravitational binding and radiative modification. The number of clouds and the volume filling factor are such that the region appears optically thin in some lines and optically thick in others. Regions of partial optical depth produce line cores and wings that blend into one another. The lines become broad not only because of Doppler motion, but because blending of multiple transitions occurs at high densities where line overlap can occur. The photon field maintains the ionization structure because any attempt of the gas to recombine fully is countered by the influx of new ionizing photons. The broad line region is therefore one of the major observational signatures of a quasar. Its existence demonstrates that there is gas at intermediate radii, whose density and ionization state place it in a regime where emission lines remain strong. In extremely distant and extremely luminous sources like the quasar associated with TON 618, the broad line region remains a powerful diagnostic tool for determining mass ionization and energy balance in the system, because the spectral lines that arise there reveal the velocities, densities, and compositions of the gas that occupies this intermediate domain. Beyond the broad line region, and still well within the gravitational reach of the central mass, lies a domain in which gas cools enough that molecules and dust grains can exist, without being instantly destroyed by intense radiation, because the temperature and ionization conditions are moderated by distant shielding and geometry. And in this region, the radiation field that escapes from the inner disk and corona is partially absorbed rather than simply transmitted, causing a significant portion of that energy to be re-emitted at infrared wavelengths as dust grains warm and then release photons at longer wavelengths that travel outward more easily, because the opacity of dust decreases at longer wavelengths. Dust grains form only where temperatures fall below sublimation thresholds, and where chemical enrichment has already seeded the gas with the heavier elements needed for solid particle formation. So the presence of dust in a luminous quasar at this redshift confirms that star formation has already occurred in earlier epochs of the host system, and has returned carbon, silicon, oxygen, and metals into the interstellar medium from which grains condense. This dust does not form a perfectly uniform ring or sheet. Instead, the dust distribution is clumpy and three-dimensional, because dense clouds, turbulence, local shocks, and leftover irregularities in the inflow create inhomogeneities in density and temperature. The dust that survives in this region absorbs ultraviolet and optical photons, heats, and then emits in infrared bands, establishing a thermal equilibrium in which absorbed power balances emitted power. The amount of energy reprocessed in this region depends on the luminosity of the central engine, the density of dust, the geometry of the dust distribution, and the extinction properties of the grains. For a hyperluminous quasar with mass measured in many tens of billions of solar masses, the incident radiation field is strong enough that dust sublimation radii may be pushed farther outward compared to less massive systems, because inner dust cannot survive near the nucleus when temperatures are too high. This sets an inner boundary for dust and molecular gas. Outside that boundary, gas densities and shielding become sufficient to allow molecules to exist. Molecular gas forms when atoms bond in cooler regions, and this gas may emit spectral lines in the infrared and submillimeter bands. Dust and molecular gas coexist in these regions because both require similar thermal conditions to remain stable. The molecular gas may include carbon monoxide and other simple molecules that can persist in the shielded clumps. The coexistence of dust and molecular gas indicates that the radiation field is spatially filtered by the geometry of the gas distribution. Turbulence can cause dust structures to shift over time. Collisions between clouds can compress dust grains and alter their shapes or compositions. Supernova enrichment from earlier star-forming episodes may influence which elements are available for grain growth. These factors create a dynamically changing opacity field that alters how radiation travels through the region. The dust-laden zones are often described statistically rather than geometrically, because the actual distribution cannot be spatially resolved at these distances. The re-emitted infrared radiation from dust becomes an important component of the total spectral energy distribution, because dust acts as a mediator that converts high-frequency radiation into lower-frequency emission. This infrared emission escapes more easily because dust opacity drops at long wavelengths. Dust and molecular gas store mass that can, in principle, continue to move inward if angular momentum drops. If the gas becomes gravitationally unstable, it may collapse further. But the dust and molecular zone is also susceptible to radiative feedback, because radiation pressure can push on dust grains. If the radiation force becomes large enough in a particular direction, dust may be driven outward and drag gas with it. Thus, this region experiences a continuous tension between inward gravitational attraction and outward radiation push. The structure of the dust distribution also influences which spectral lines escape from deeper layers. In directions where dust is optically thick, the lines generated in the molecular gas beneath may be blocked, while in directions where dust is optically thin, lines may escape more freely. Because dust grains absorb and scatter photons, they also influence polarization. Scattered light becomes polarized. Measurements of polarization in quasar light often reveal signatures consistent with scattering by dust, and these signatures imply certain symmetries in the dust distribution. These symmetries may reflect the net angular momentum of the host or the geometry of inflow. The molecular gas may form in clumps stabilized by self-gravity, and within those clumps the gas may cool enough to form complex molecules. If the clumps remain shielded long enough, they may continue to cool, but this cooling competes with radiative heating from the central engine. The infrared emission from dust reveals that matter in this region retains memory of both the central luminosity and the thermal conditions of the region itself. The physics in this region also influences star formation, because if molecular gas becomes dense enough, it may collapse into new stars, but if radiation heating prevents further collapse, star formation may be suppressed. Thus, star formation may be patchy in this domain, occurring only in the best shielded clumps. The existence of dust and molecules at these radii therefore reflects a balance between radiation from the nucleus gravitational binding turbulence and optical depth. This region is not an inert byproduct of the bright inner disk. It is a co-evolving component of the system which both absorbs and reprocesses the energy from the central engine and simultaneously acts as a potential inflow channel, because dust may serve as a cooling catalyst, allowing molecular gas to lose heat more efficiently than atomic gas alone. The dust and molecular domain thus plays a twofold role. It is a radiative buffer that filters the emergent spectrum and an outer inflow reservoir that can deliver matter further inward if angular momentum loss continues within these clumps. In a hyperluminous quasar environment, this is a crucial zone of thermal regulation, where the interplay between heating, cooling opacity, and gravitational structure produces a layered distribution of temperature and density that defines which wavelengths can escape most efficiently. As the inflowing material progresses still farther inward, its orbital velocities continue to increase, because gravitational binding energy increases as radius decreases, and in this regime the physics shifts from the domain in which molecular and dust-mediated thermal regulation dominates to a domain in which the flow becomes more ionized, hotter, thinner, and strongly influenced by differential rotation on scales, where stable orbits represent the last radii at which matter can remain in gravitationally bound circular motion without plunging toward the central mass. These radii are known as the innermost stable circular orbits, and their existence is not a function of gas chemistry or cloud structure, but of space-time curvature itself, because near a massive compact object, gravity can no longer be described by Newtonian approximations alone. The position of the innermost stable circular orbit depends on the spin of the central mass, because rotation modifies the geometry of space-time and changes the radii at which stable circular orbits are permitted. In a non-rotating case, the innermost stable circular orbit sits at a radius that corresponds to several gravitational radii, but when the central mass spins rapidly prograde, orbits can remain stable at smaller radii, and retrograde orbits become unstable at larger radii. The dependence of stable orbit radius on spin means that the distribution of matter in the very inner region depends on the angular momentum of the central mass, and this sensitivity to spin is directly tied to energy conversion efficiency, because matter that can orbit stably closer to the event horizon can fall through a greater gravitational potential drop before crossing the horizon. That greater drop yields more convertible energy per unit mass. Thus, the physics of innermost stable circular orbits exerts a direct influence on luminosity. These innermost radii represent the boundary at which matter that has lost sufficient angular momentum begins to transition from a circularly supported orbit to a plunging trajectory. The flow remains rotational, but can no longer maintain circular balance. Once inside this boundary, the gas can no longer hover in persistent orbit. It must fall inward. The gas at these radii remains so hot and ionized that atomic line opacities are not relevant in the same way they are in the broad line zone or dust zones. Instead, electron scattering remains the main opacity channel, and magnetic fields remain dynamically relevant. The strong gravitational field causes the disk to become more compact vertically, because vertical pressure gradients compete against tidal gravity that increases steeply as radius decreases. In radiation pressure-dominated zones, this vertical structure may still be supported by the outward push of trapped photons, but in any case the disk becomes more relativistic in its orbital behavior. Time dilation effects influence observable spectral features. Material in the innermost stable circular orbit has orbital velocities that are significant fractions of the speed of light. These velocities produce extreme Doppler shifts, and gravitational redshift shifts the energy of photons that escape. Observed energy distributions must account for these relativistic effects, because failing to do so results in underestimating the gravitational potential drop and misinterpreting spectral line centroids and widths. The curvature of spacetime at these radii produces frame dragging if the black hole spins and frame dragging forces matter to rotate in the direction of the black hole spin, modifying the angular momentum distribution of the innermost flow. This dragging is subtle at large radii but becomes important here. Because the central mass of the object associated with TON 618 is measured in tens of billions of solar masses, the physical radius corresponding to a gravitational radius is large in ordinary distance units. So the innermost stable circular orbit occurs at a large physical size, even though in gravitational units it is small. This means the region where relativistic orbital mechanics dominate extends across distances far larger than the scale of stellar-scale accreting objects. The innermost stable circular orbit thus encloses a disk region that is physically vast, filled with ionized plasma, rotating at extreme velocities and emitting radiation drawn from the last stage of gravitational energy release before matter crosses into the plunging region. The thermal conditions inside this zone reflect competition between viscous dissipation, radiative cooling, and relativistic energy gradients, producing extremely high temperatures attuned to ultraviolet emission in rest frame, and contributing indirectly to high-energy photon production through further scattering interactions. Because the gravitational potential is so steep near this radius, the energy being extracted per unit in falling mass is near its maximal allowable efficiency for thin disk accretion. Both radiative efficiency and temperature profile depend on where this boundary lies. The innermost stable circular orbit therefore represents a structural hinge connecting the thermal disk to the plunging region that leads toward the photon orbit zone and event horizon. It is a structural threshold that marks the last radius at which inflowing matter can remain in a quasi-stationary circular state. Inside it, the flow must plunge inward and can no longer release energy by orbiting on stable circles. The existence of such an orbit is a fundamental property of relativistic spacetime geometry. In this region, the abstract principles of general relativity become operational in the most practical possible sense, because they define not only motion, but energy yield and luminosity. The accretion disk transitions here from a radiatively efficient region to a region where gravitational energy is no longer fully extractable. Observational properties of quasars depend critically on these radii, because the emergent spectrum is shaped by how close matter can orbit before plunging. In extremely massive quasars, these radii scale upward relative to physical units, and yet remain the decisive determinants of energy budget. This domain is therefore a hinge in the structure of the flow, because it converts the inward migration of matter from gravitationally regulated rotational motion to unstable plunge. Inside this radius, matter cannot resist the inward pull. It must fall inward, and the nature of spacetime at these radii sets the stage for the ultimate non-return boundary still deeper in. Still farther inward than the innermost stable circular orbit, there exists a special relativistic radius, where photons themselves can orbit the central mass, because spacetime curvature bends light into closed circular paths, and this region is known as the photon sphere. A domain where the gravitational curvature is so strong that even massless particles move on null trajectories that curve tightly around the central object rather than escaping outward in straight lines. These circular photon orbits are not stable in the classical sense, because the slightest perturbation in direction or energy will cause the photon either to spiral outward and eventually escape, or to spiral inward and cross into deeper radii, so the photon sphere is a dynamical boundary defined not by stationary permanence, but by the possibility of light existing momentarily in looping paths. It is not an optical surface, nor is it a physical structure made of matter. It is a geometric property of curved space-time. The location of the photon sphere depends on the mass of the central compact object, and on its spin because rotation modifies the geometry of space-time and can alter the radii at which circular photon trajectories exist. In non-rotating cases, this radius sits at a predictable multiple of the gravitational radius, but in rotating cases the radius depends on whether photons are orbiting in the same direction as the spin or in the opposite direction. The photon sphere region marks the transition between where light can escape outward without extraordinary bending and where light can be forced into nearly closed loops. Photons emitted slightly outside this radius can escape outward, but may be strongly deflected. Photons emitted slightly inside this radius have trajectories that lead them inward. The result is that this region forms the last location where light can be temporarily confined by curvature. In a very massive system with mass measured in many tens of billions of solar masses, the photon sphere corresponds to a radius that in physical units remains extremely large compared to stellar-scale black holes because gravitational radius scales linearly with mass. Thus, the geometric region associated with photon orbits spans a distance that is enormous compared to the physical sizes of stars or ordinary astrophysical structures. Near the photon sphere, the curvature of space-time modifies the way radiation emerges. Photons climbing outward from deeper within the gravitational potential lose energy because of gravitational redshift, and those that originate near the photon sphere experience strong curvature effects. Gravitational lensing of light near these radii produces paths that wrap around the central mass, such that the image of emitting regions may be amplified or distorted even if the disk itself is axisymmetric. The existence of this region influences the appearance of quasars because the photon sphere defines a boundary where the geometry of radiation escape changes rapidly with radius. The observed light from very deep radii may be dimmed not because it is absorbed, but because gravitational redshift shifts its wavelength downward and reduces its energy as observed at large distance. Light that emerges from regions just outside the photon sphere undergoes significant bending, so the apparent brightness distribution around the nucleus can be influenced by this geometry. Although this photon orbit region does not contain matter, it influences the flow just outside it, because matter approaching from slightly larger radii remains in a region where the gravitational potential is steep enough that orbital velocities approach significant fractions of the speed of light, and radiation escape becomes inefficient. Photons produced very near this radius are subject to strong energy shifts that shape the emergent spectrum. The bending of photons creates the conditions under which the apparent interior boundary of observable structure acquires an apparent outline. In the case of extremely massive quasars, the photon sphere may be physically vast in meters or kilometers, but in gravitational terms it remains close to the horizon. This region imposes a geometric limit on how much information from inside can be transmitted outward, because photons that originate just slightly inside the photon orbit cannot maintain stable outward trajectories. The photon sphere thus is not a feature of the disk, or the corona, or the broad line region, or the molecular domain. Instead, it is a direct expression of gravity operating on light rather than on matter. The curvature here is so extreme that light loses the intuitive property of travelling in straight lines. Instead, it navigates space-time structured by the mass at the centre. If photons in this region are emitted isotropically, their emergent distribution will not be isotropic because of this curvature. Some photons will fall inward and be lost. Others will scatter or orbit before escaping. This condition influences the efficiency with which light from the innermost radiating gas can emerge to distant observers. It is also a region where inward plunging matter transitions into a domain where no stable circular motion remains. The photon sphere marks a final surface at which light can exist momentarily in orbit, but cannot remain sustained. In the geometry of such a massive system, this radius forms a natural outer boundary to the domain in which no outward directed trajectory can avoid bending into paths of extreme curvature. It sets the threshold where the escape of photons becomes highly sensitive to initial conditions. In extremely luminous quasars, the photon sphere plays its role quietly because it is not a source of new emission nor a regulator of inflow, yet it is a crucial geometric boundary because it establishes the final optical domain before the region from which no photons can emerge at all. Inside the radius, where photon orbits are even theoretically possible, there remains the final boundary at which space-time curvature becomes so strong that no outward directed light path, no matter how energetic, can carry information into the wider universe. And this boundary is the event horizon, a surface that is not a material barrier made of atoms or plasma, but a geometric threshold defined entirely by the structure of space-time, in which the escape velocity equals the speed of light and beyond which causal connection to the external universe is lost. Matter that has spiraled inward from the disk and past the innermost stable circular orbits will plunge across this boundary in a finite proper time, and will not slow or linger, because the space-time inside this radius does not allow orbital support, so the flow crosses the horizon as a final irreversible step in which gravitational potential energy is no longer accessible to the outside, and the history of the matter becomes permanently hidden from external view. The horizon radius depends on the mass of the central object, and in the case of a supermassive system measured in many tens of billions of solar masses, this radius is enormous, not in gravitational units, where it remains only a few gravitational radii, but in physical units, because the gravitational radius scales linearly with mass. A horizon corresponding to such a mass occupies a region in space large enough that the physical scale of this boundary is not microscopic or stellar-sized, but astronomically significant, large enough to exceed the orbits of planets in planetary systems, large enough to rival the size of the solar system. In such a system, the horizon becomes a physically vast frontier, even though nothing at that frontier emits light. The boundary is located where outward-directed null geodesics cannot turn outward anymore, and because general relativity treats gravity as curvature of space-time rather than a force field, the horizon is simply the place in space-time where light cones tip inward so completely that all future directed paths lead toward the singularity. Photons that originate inside the horizon cannot move outward, because outward null trajectories are geometrically impossible. For matter that passes inward, the passage across the horizon is smooth, because the horizon contains no matter, no shock and no discontinuity in any physical field that matter can detect locally. Locally, the crossing is unremarkable. The dramatic property of the horizon is not local but global, because it defines which regions of space-time can communicate outward. In high-mass systems, tidal gradients at the horizon are smaller than in lower-mass systems, because tidal forces scale inversely with mass at the horizon radius. So in extremely massive quasars, tidal stretching at the horizon may be relatively mild over macroscopic dimensions. The event horizon, therefore, is not a violent tearing surface, but rather a gentle frontier in local physical terms, even though it represents the ultimate boundary in global causality. Radiation that originates just outside the horizon must climb outward through a steep gravitational potential, and gravitational redshift shifts the energy of such photons downward as they escape, making emission from very deep regions appear dimmer and redder than emission from outer disk radii. This redshift is one of the reasons the innermost disk emission is difficult to recover observationally. In systems at extreme redshift, the cosmological stretching of wavelengths compounds the gravitational stretching imposed by the deep potential, so the final spectrum carries multiple layers of redshift imprinted by cosmology and by gravity. The horizon region in the quasar associated with TON 618 therefore is not simply a conceptual limit, but a domain in which radiative efficiency drops to zero because no outward energy transfer is possible. The disk extracts as much gravitational energy as allowed before matter crosses the horizon, and beyond that crossing nothing further can contribute to luminosity. This is why the horizon sets a natural limit on how bright any accreting system can be. The horizon also defines the region beyond which one cannot obtain information about the interior by observing outbound light or particles. The geometry of the horizon in rotating cases is not spherical in the same sense as non-rotating cases, and spin modifies the shape of the horizon, because rotation drags space-time around the singularity. If the central mass rotates, the horizon becomes ablate in Boyer-Lindquist coordinates, and the ergosphere that exists outside the horizon is a region where frame dragging is so strong that no object can remain stationary with respect to distant stars. In extremely massive systems, this ergosphere zone occupies a large physical region. In principle, rotational energy can be extracted from black holes through processes that operate in the ergosphere, and if such extraction is coupled to magnetic field lines anchored in the disk or corona jet launching, may be influenced by this rotational channel. But once matter crosses the horizon, this potential is no longer accessible. The horizon absorbs everything that crosses it. No signal emerges. It is the absolute boundary of observational relevance. The enormous horizon radius of such a massive system means the conversion of gravitational potential energy is distributed across a vast domain just outside the horizon, where photons struggle to escape. Inside the horizon, space-time inevitably guides everything toward the singularity that lies at the center, although the precise nature of the singularity cannot be probed directly because no information can return. The existence of the horizon means that the ultimate stage of inflow is a domain that is physically present yet observationally silent. In the context of the quasar associated with such an extreme mass, this domain is the final endpoint of cosmic supply. Everything that the cosmic web delivered, everything that angular momentum transport drove inward, everything that radiation pressure failed to deflect, everything that magnetic fields fail to stall, eventually crosses this boundary. And because the luminosity observed is the integrated result of energy extracted prior to this crossing, the horizon is the structural boundary that sets the limit on how much power can be extracted from infalling matter. The horizon completes the inward journey, marking the last possible frontier of observation, and the boundary beyond which the physics of the inner structure of space-time remains hidden, not because of opacity or absorption by matter, but because the geometry of space-time itself enforces that no communication from within can reach beyond.